Welcome to Lesson 30, Graphing Functions for Mrs. Boyle's math class. We're going to start off by just talking about what a linear equation is. We're going to be looking at several different kinds of graphs today, but just introducing what a linear equation is and a linear function. A linear equation is an equation whose graph is a line. And that comes directly from the word linear, which has the word line in it. So it's an equation whose graph forms a straight line. A linear function is a function whose graph is a line. So an example of that, an example of both would be y equals mx plus b, or if we were to put it in function form, f of x equals mx plus b. You should recognize this equation, which is slope-intercept form, where m represents slope and b represents the y-intercept. So an example of that in actual numbers would be y equals 5x plus 3, or f of x equals 5x plus 3 if we were to put it in function form. Alright, so let's look at a couple of graphs. First one we're going to look at is y equals 2x minus 5. We're going to graph this equation by filling in x values. I usually try to put 0 in the middle of my table of values and then do a couple negatives and a couple positives for x. So if we fill in negative 2, we're going to have y equals 2 times negative 2 minus 5. So 2 times negative 2 is negative 4, and negative 4 minus 5 is negative 9. If we fill in negative 1, we'd have 2 times negative 1 minus 5, which would be negative 2 minus 5, and that would be negative 7. If we fill in 0, we would have 2 times 0 minus 5. And 2 times 0 is 0, so 0 minus 5 is negative 5. And this is in slope-intercept form, so this negative 5 is the y-intercept, which represents when x equals 0, if we're going to graph that point. Over here on the graph it would be 0, and then down to the negative 5. So that's where it crosses the y-axis, that's why it's called a y-intercept. But this you should already know. Okay, 2 times positive 1 minus 5 would be 2 minus 5, which is negative 3. And 2 times 2 minus 5 would be 4 minus 5, which is negative 1. So we're going to graph all these points. Some of them aren't going to quite fit on our graph. So I'll start with, I already graphed 0, negative 5. I'll start with 1, negative 3. And 2, negative 1. And then negative 1 is negative 7 on the y, which would be right about there. Why is it doing that? Okay. So if we were to connect these lines, or dots, I mean, we would have a straight line. So this is a linear equation. Right, moving on to the next example. We have y equals 3x squared. So again, we're going to fill in some x values. We're going to pick a couple negatives and a couple positives. So if we fill in 3 times negative 2 squared, that would be 3 times 4, which is 12. And if we fill in 3 times negative 1 squared, that would be 3 times 1, which is 3. If we fill in 3 times 0 squared, that's just going to be 3 times 0, which is 0. And 3 times 1 squared is going to be 3 times 1, which is 3. And 3 times 2 squared is going to be 3 times 4, which again is 12. So if we graph these points, we'd have negative 2, 12, which doesn't fit on my coordinate plane here, according to how it's labeled. But I can fill in negative 1, 3. And I can fill in 0, 0. And 1, 3. And then 2, 12 again would be off. So if I connect these points, whoop, missed the die. Okay, if I connect those lines, sorry about the messiness here, you can tell no matter how messy it is that this is not a line. So this is non-linear because it doesn't form a line. It actually forms what is called a parabola because it's a quadratic equation. We'll get to that later. Okay, moving on to the next example. We're going to match each graph with one of the tables here. So we're going to start looking for some of these points. In this first rule, f of x equals 3x minus 1, I'm going to view these as coordinates. So the x value is negative 2 and the y value is negative 7. So another one would be 0, negative 1. So I'm going to start looking for these points. So on the graph A, at x value 0, it goes to positive 1, so I know it's not that. And in graph B, it does go through 0, negative 1. Let's check negative 2. So negative 2, negative 7, that's another point on the line. And if we check another one, we could check 2, 5. So over 2 and up 5, which is right here. Oops. So that's another point on the line. So I'd say this is pretty close. So table 1 would be graph B. Alright, moving on to the next example. F of x equals negative 2x plus 6. Again, we're going to start looking for some points, so we'll look for 2, 2 here. So let's see. Graph A is pretty close to 2, 2, but not quite. Graph C goes through 2, 2 right here. Let's try another one. 1, 4. We'll look for that one. So let's see if that's on this line as well, and it is. So that's 2 for 2. And we'll check one more, negative 1, 8. So negative 1, 8 would be right here. And that one's on this line as well. So that's pretty good indication that this is graph C. And that leaves table 3 for graph A, but just to be sure, we'll check some points here. So we'll check negative 3, 0. So back negative 3, and it crosses the line right at 0 there, so that's good. And 0, 1. So 0 on the x, and it goes through the y-axis at 0, 1. So that's good. We've matched them all up. The next example, we're going to match each graph with the two equations. Now if we go back to these other lines here, you can see that all of these functions have a coefficient with x, a coefficient with just an x, a coefficient with just an x. And you can see that all of their graphs form straight lines. So if we go to this one, we have a coefficient with just an x, not an x squared or an x cubed or an x with another exponent, just x. So we can probably make a good prediction that that goes with graph 1 because it's a straight line. But just to be sure, why don't we plug in a couple of points? So we'll try 0, -4 is one of the points on the line. So if we fill in 0 for x, we would have 5 times 0 minus 4, which would be 0 minus 4, which equals -4. So that is correct for that point. And then we'll try one more point here. I can see that this crosses 1, 1. So we can try 5 times 1 minus 4. So 5 times 1 is 5 minus 4 equals 1. So the point would be 1, 1. So there's another point. So that seems to work so far. So we'll match graph A with the first graph here. If we look at the second graph, you should notice that this has an x squared in it. And if we go back to our original graphs on the first page, you can see this one also has an x squared in it, and it forms what's called a parabola. So if we go back to number 3, this also forms a parabola. So we'll match graph B, equation B with graph 2. Okay, the next set of examples here, we're looking for the domain and range of each function. Remember that domain is x values, and range is y values. Okay, so in this first graph, we don't even need to worry about the equation that's going with it. We're just going to look at what's graphed on the coordinate plane. You can see here, if we're looking at x values go left to right on the x-axis. So you can see that the line stops at a certain point here, and it actually stops at the y-axis, which is x equals 0. But it goes on in this direction for we don't know how long. We'll say forever. So the domain would be x is either going to be greater than or equal to 0 all the time. If we were to shade that in, I like to show it by shading, it would be everything from this point on. Now if we look at the range, we're going to use a y to show this. And you can see that this line stops at y equals 1. And it goes up from there. If we were to shade that in with a different color, it would be everything above that line. So that would be y is greater than or equal to 1 for the range. Okay, moving on to another example down here for B. The domain is going to be x values. And you can see, if we're using pink for domain, that it doesn't stop in either direction. It keeps going here, and we know that it keeps going because this line doesn't stop. It's going to keep going on forever to the right, and it's also going to go on forever to the left. So the domain is actually all real numbers. If you remember the symbol for that, it's the R with a double line. For the range, we're looking for y values. And the y values are also going on forever to the top in the upward direction and forever downward in this direction. So the range is also all real numbers. So moving on to the third example here. For the range, the domain, the x values. The x values are going to go on forever to the right. They're not stopping. And they're going on forever to the left. They're not stopping. So that's all real numbers again. And the range, I'm going to have to stop really quick. and pick up in part 2.